Very good. Hello, everybody. So let's get a quick reminder of what we discussed in the last lecture. So we talked about entanglement in the context of bipartite systems. So we have a joint system which we can think about as a tensor product of two subsystems, and we have a pure state that we're considering at the moment. And that pure state can always be written in a so-called Schmidt decomposition. Okay. And these are so-called Schmidt coefficients. They are positive numbers. Well, they're actually positive. That's 0. And these are the Schmidt vectors. And this is sometimes called the Schmidt rank. Okay. So this is a general form that we can always write, and it's the most important thing we need to know when thinking about entanglement in the context of bipartite systems, okay, the pure states. So what are some of the things that we learned last time about this Schmidt decomposition? Well, one thing is if I look at the marginals, that is to say the state of subsystem A and subsystem B, they have the same spectrum. Where the spectrum, that is to say, the eigenvalues of the density matrix are related to the squares of the Schmidt coefficients. And the eigenvectors of the marginals, the reduced density operator, are the Schmidt vectors up to some phase which we cannot get from the marginalization, okay? And most importantly, or at least one of the most important things, is that the degree of entanglement depends on this probability distribution. Right? So these are, of course, I can think always of the density operator as a statistical mixture of its eigenvectors, weighted by the probabilities given by the eigenvalues, right? So these p's form a probability distribution normalized to 1, and that probability distribution determines the degree of entanglement, right? So if I had a pure state, then, well, this Schmidt rank would be 1, and it would just be a product state, and I'd have pure states for the marginals. So the degree of entanglement is related to the mixedness of the marginals. Okay? And we like to be fancy and quantify that degree of entanglement in terms of the amount of missing information about the whole when we only have the parts. Okay? So the degree of entanglement we call E is then given by the entropy of this distribution. So the entropy of a probability distribution, which is this object, and we could measure it in any base we like. Typically these days we like to measure it in base 2, so we think about it as bits, is equal to the amount of missing information in the parts. So it's how many bits of information I would need to specify the whole state. That's what the entropy measures, which is often written as in an operator form as minus trace log rho, either for either marginal, because they have the same entropy. And that, written this way, it's known as the von Neumann entropy. Okay, so the von Neumann, this is an operator expression, but if I look at the trace in the basis of its eigenvectors, I get this, right? That's what that means, right? So there are lots of degrees of entanglement. Any measure that is monotonic with E is known as an entanglement monotone. So I can look at, for example, as was suggested, just the purity, the trace of rho squared of the marginals. That's an entanglement monotone. Importantly, the amount of entanglement doesn't change if I do something, if I locally change one of the systems. If I interact with some magnetic field on a spin locally, I cannot affect the amount of entanglement. And if I call someone on the telephone and say, hey, I did this, you do that, I can't change amount. That's classical communication. So an entanglement monotone is unchanged by local operations or classical communication. I need some kind of quantum interaction to create entanglement. So the other thing we discussed last lecture was the idea of an entangling interaction. So if my Hamiltonian for the joint system acts just independently, there's some Hamiltonian for system A and some Hamiltonian for system B, this is separable. That is to say, the unitary is separable. Okay. On the other hand, when does not equal a sum of the two, which I'll just write like this without the tensor products, then the U does not equal what we would call, these are sometimes called local unitaries. The notion of local here is just a statement of subsystem A versus subsystem B. At the moment, it's not about space, time, locality, but we'll come to that in a moment. And so any time I have an interaction between the two subsystems, then I will generate entanglement. Okay? Now you might say, boy, that sounds easy. Why don't I just well, entanglement sounds, just let them interact. No, we've got some entanglement, let's use it. Yeah, but as we will see, sometimes entanglement's not a good thing. Because sometimes everything gets entangled with everything else, and then what's left is a mixed state. We'll come back to that. So, in some sense, the fact that everything entangles with everything else is a problem. Okay? Isolating the interactions you want so that you get the entanglement you want without having it entangle with everything else that you don't want is the whole problem. Or maybe it's the solution, I don't know. But it is the facts of the universe. Okay? Very good. All right. Maybe I'll use this board here, and we'll continue here. So let's talk about entanglement and the quantized electromagnetic field. So, when we think about the quantized field, of course, the degrees of freedom are not always so obvious. We got particles, and we got waves. And we can think about entanglement relative to these different kinds of degrees of freedom. Okay? So in particular, the easiest kind of conceptual thing that we might think about is I might think about, say, two photons. Okay? Let's just think about that. And we can think about, for example, the spin degree of freedom, which of course is the polarization of the photon. So loosely, and we're going to come back to this in a moment to be a little less loose, I can think, okay, I have two photons. Each photon can have two polarization states if I look at its polarization relative to its propagation. So I can think about this as two qubits. And so my joint Hilbert space for the two photons would be, the Hilbert space is associated with two spin 1/2 particles. Of course, we know that the particles are, the photons are spin 1. This is just a mathematical mapping onto the two polarization states, right? So I can think about this, if I was being loose about it at the moment, putting my hands on the hips never works to keep it to do what I want to do, but I do it every time. All right. I need anti-grease on these things. All right. So I could think about the tensor product space which you will see in papers written in terms of, say, a horizontal and a vertical polarization. So we might think about this as H tensor H, H tensor V, V tensor H, and V tensor V as my product basis. Okay. And yeah.
So these are still distinguishable photons?
Oh yeah, you're getting ahead of the curve here. So let's hold off on that thought for a moment. The answer is yes. I have to think about them as being what I'm calling this A versus this B is really, let me actually, for the moment, I have my notation on it. Let's call this photon 1 and photon 2. What I'm calling photon 1 and one I'm calling photon 2, I'll come back to this. Let me go back here. There are two photons, we'll call them A and B. Come back to the 1 and 2. Let's hold off on this thought for the moment. Let's just treat them as distinguishable. Okay? So two photons that are distinguished. Otherwise, this is meaningless. You're right, Matt. Come back to it in a moment. Okay? Right. So, with all those caveats that I have been swept under the rug at the moment, I could say that the polarization state of these two photons would generally be some superposition of those basis states, right? And then I can think about the entanglement by looking at the singular value decomposition of this and look at a Schmidt decomposition of this into the kind of thing we just wrote down, right? And what's the maximum possible value of mu max? 2, right? So in principle, I could have one e-bit of entanglement, right? I could have something that looked like a spin singlet here, for example. Now that comes to the point that Matt was raising, which I'll elaborate on more now, which is the fact, of course, the photons are bosons, generally indistinguishable particles. So what exactly am I talking about when we write this down? Because somehow I haven't dealt with the fact that in principle, I have to think about a state that is symmetric under the exchange of the two photons, right? And in principle, I could have any superposition I like that doesn't look, I can look like, I can have this state plus that state. That state wouldn't, this state plus this state. That state wouldn't be symmetric, it seems, under. Now, of course, as you know, it's exchange under all the quantum numbers in both this position, or I should say the motional degrees of freedom, and the spin degrees of freedom. So right here I'm just talking about the spin degrees of freedom. So when we write this down, as Matt suggests, we are thinking about the notion of distinguishable photons. But in what way could they be distinguished? Well, they could be distinguished in the following sense. So I have also motional degrees of freedom. Of the photon. Right? So the photon has momentum as well. So when we write this down, this is a kind of first quantized notation, where we think about these as particles in the same way that, we think about the electron and we think about its, say, the spin of the electron, right? Spin up and spin down, and we write down a spin state. But we can think about a second quantized notation. Okay, where I have a creation operator that, say, creates a photon with a particular momentum in a particular polarization state, right? And so if I applied that to the vacuum, I'd get one photon with that momentum and that polarization, right? Or I could create a photon in the vertical polarization, for example. Okay. So now let me consider the following thing in second quantized notation. So what have I written down here? So now I have two photons. One of the photon has momentum K1 and some polarization, where this goes over H or V. Okay. And the other photon has momentum K2, and it has polarization epsilon, well, let me call it 1 and 2. Better notation. So I have two photons, a photon A and a photon B, but I don't know which photon is which. I know one of the photons definitely has momentum K1. The other photon definitely has photon K2, but I don't know whether that is photon A or photon B. Because this, if I commute these, is the same state. So this state, because of the fact that these commute, respects the Bose symmetry. Okay? But I can have the same matrix that I had here. Okay. So this is the second quantized version of this that respects the symmetry. Now if I wanted to write the full wave function for the photon, what I would say is, okay, one of the photons is in this plane wave. The other photon is in that plane wave. It has that for photon A and photon B, or this is my two-photon spinor wave function. Let's analyze this and understand what's happening here. There are two photons, photon A and photon B. I don't know which is which. This two-photon state is symmetric under exchange of both the spin and the spatial degrees of freedom of A and B. Do you agree with that statement? If I change A to B, this state is exactly the same. However, there is definitely a photon with momentum K1. And there's definitely a photon with momentum K2. And the one with momentum A1 has this polarization. It always has polarization epsilon 1. And the one with momentum K2 always has polarization epsilon 2. And what I would do is I would sum over all the probability amplitudes for that. And when I do that, I have this state. Notice, if I just had one of these, the bow symmetry makes it look like that is entangled, but that's not an entangled state of any use. I need to have a superposition, because what does this represent? Let's say that this is photon K1, and this is photon K2. I mean, there's two photons. I don't know which is this is A or B. But I know that one of them has momentum K1, and that one has polarization epsilon 1. The photon in that mode has polarization epsilon 2. If I just had that, if it had a definite epsilon 1, epsilon 2, that's not an entangled state, even though from the point of view of, so I just had one amplitude here, it looks entangled, but that's not. That's just Bose statistics. When we say it's distinguishable, it's saying the photon that is in this mode, I don't know whether that's A or B, but it's the one that when I put my detector, I'm going to see that guy. They're distinguished by their spatial degree of freedom. In this case, their momentum. And there's a photon here. And so it's the Schmidt rank of this that determines the entanglement. That's how we deal with the entanglement of identical particles. Great. Okay, very good. So we could also think about the entanglement not in the spin degrees of freedom. We can think about entanglement in the motional degrees of freedom. Of the photon. So here's an example state written in second quantized form. Let's take a look at this state. What have I done? I've created, this state has two photons. Do you agree with that? Yeah, I've created two photons. This creates a photon in a plane wave with a certain polarization with momentum K1. This creates a photon in a plane wave with, in this case, the same polarization. I didn't have to be, but I did. And K2. But then I have a probability amplitude for having both K1 and K2. And now I'm summing, integrating, over all the probability amplitudes for K1 and K2. Okay? So, the motional entanglement, this is a two-photon wave function. Of course, if I wrote it in first quantized form, I'd have to say either Ka is equal to K1 and Kb is equal to K2, sum with Kb equals K1, Ka equals K2, right? But written with this in the second quantized form, I don't have to symmetrize everything because the creation operators take that into account. Okay, so very good. So now the question here is, I can take this two-photon wave function for particle A and B, and I can write it, even though this lives in an infinite dimensional Hilbert space, in a Schmidt decomposition. Where these are the Schmidt eigenfunctions. For example, they might be Hermite Gaussians. They might be Laguerre Gaussians, which we would call orbital angular momentum states. And so this represents entanglement between the spatial mode of the photons. I could say the one photon is in TEM00, the other one is in TEM01, or the other one is in TEM00, the other one is in, I don't know which one. That would be an entangled state relative to the spatial mode degrees of freedom of the photon. Okay? Now, what's the maximum value here? What could it be? It could be infinity, right? Now, of course, such a state would never, I mean, it'd have to, the Schmidt coefficients, if this is going to be a normalized state, even though there might be an infinite sum, the sum of the squares has to be 1, so it would not be something which would have equally weighted probability on an infinite dimensional ladder unless it's an unphysical state, right? But I could have a lot more entanglement, in principle, in a Q dit, where D is big, than in a Q bit. And people are looking at that, like our very own Professor Becerra, who is thinking about entanglement in the orbital angular momentum mode of photons, and how much more entanglement you could generate that way. Cool. Yes, sir.
Yeah, I have a doubt in this.
Uh-huh.
Yeah. So we have two photons.
Yes.
So if you measure one of the photon is in momentum from K1,
Yeah.
we know the other photon is in K2, right?
That's correct.
So why is not that entanglement? Is it not similar, like if you measure spin of one is up, we can say that.
Oh, because, well, I have to have a superposition. So let's say I have, there's a, if I know for sure that one of the photons, there, you have to have two different alternatives, right? So if you're right, if I had a situation where there are two photons where either one goes there and the other goes there, or the other way around, right? So the question is, what, how do I want to state this? So one of the photons is going off in momentum k1, and the other one is going off in momentum k2. I don't know which is which, right? But there is no useful missing information. What other measurement can you do in what other basis by which you would project, if you're only going to measure K1 or K2, that's only one measurement you can do. So in order to see the missing information, you have to have two orthogonal possible bases. Like when we had the spin singlet, right? Where I can measure either, I can measure, say, in the x basis or the z basis and see the interference between alternatives. There's no interference between different alternatives. There's only one alternative here.
Yeah, just a momentums.
That's all there is. The fact that they're identical particles has no implication in this context for two different alternatives. There's only one alternative. This guy is in there, and there's in there. There's no other two alternatives.
But in this case, we have different modes. That's why we have the entanglement here.
Well, it wouldn't be entanglement. So if this state, let's say I had this state. That's a product state. That would be no entanglement. Now, the symmetrization, once I put it into first quantized mode, I'd have to symmetrize the wave function. But if this thing were equal to that, that's a product state.
So
Right.
that's the situation here, basically.
Yeah, this would be that case. I need to have a non-zero, something beyond a rank 1 Schmidt decomposition in order to have entanglement. It is very confusing when we think about it, and we've argued about this for years, whether identical particle statistics just is entanglement. But no, it's no useful entanglement at all. You have to have multiple alternatives for the case in order to have useful entanglement. All right, continuing on. So, here's an interesting question for you. Let's say I have a single photon. On a beam splitter. Okay. So here's a beam splitter. I put a single photon on this beam splitter. Let's say the photon has momentum k1, thought about in a first quantized form. Okay? So then the photon can be transmitted. Let's say it's a 50-50 beam splitter. It can be transmitted or it can be reflected and have a different momentum. Right? And so we would say psi in is that plane wave, and psi out is a superposition of two plane waves. Right? Yeah.
Is the optical phase shift different in the quantum sort of phase between them?
No, no. So, I mean, if I have some kind of matrix for, transmission from one to one, some reflection from and reflection 1, 2. Those phases in the classical are exactly the same phases, as we will remind ourselves in a moment. Yeah?
Don't we get an eye on the reflection?
Not necessarily. So let's, for example, take, I'll make a symmetric. Let's use this beam splitter because it's more easy to deal with. That's a fine unitary matrix. It's just one that's not the same for both directions. That's a perfectly good scattering matrix. It's one that would be coded different on one side than the other. Okay? So let's take this as our 50-50 beam splitter. Good. All right. So, is this an entangled state? No. It's just a single photon that's in a superposition of two plane waves, just like we had in elementary quantum mechanics. You think about something, this is an eigenstate of momentum, and this is something that's in a superposition. It's one particle. Or is it an entangled state? That's an interesting question, because suppose I look at this in second quantized form. So suppose I say, all right, I have two modes, 1 and 2. Okay? And I have a creation operator for mode 1 and a creation operator for mode 2. So this creates a photon with momentum k1, and this creates a photon with momentum k2. Okay? So my input state in this notation would be that, right? Which is 1 photon in mode 1 and 0 photons in mode 2. Right? What is my output state? Well, I have to apply the scattering operator to the input state. That's the S matrix. Right? Which is this transformation, the unitary transformation on that, which is, as you remember, the same transformation on the creation operators as the classical amplitudes. You remember that? So this is equal to, that's a dagger, by the way. That's actually the vacuum, sorry. That's it, vacuum. Which is 1 over root 2, 1 photon in mode 1, and the other photon in mode 2. Okay. That's really a fancy way of saying this in first quantized form. But if I was somewhat suggestive and to think about two modes, kind of looks like an entangled state. Is it an entangled state? Or is it not? Yeah.
It's So does this have to do with your measurement? Like if you're measuring the momentum of a particle in that basis is non-entangled, but then in the, like, if you're able to measure the modes, not the momentum of.
If you're ready to measure the number, right, yeah. So what's important here is what degrees of freedom are we talking about? Here I'm talking about modes, and here I'm talking about particles. This is what we would call wave entanglement. I can think about my electromagnetic field's degrees of freedom as a tensor product of modes. So if I thought about it, we had a bunch of simple harmonic oscillators for some number of modes. Where, n goes from 0 to infinity for each mode. Then I think about the modes as a degree of freedom. The question is this useful entanglement? Well, let's do a particular Gedanken experiment. Suppose I have the following thing. Let's say I have a single photon incident on this beam splitter. Can either be transmitted or reflected. And inside this, I'm going to put a cavity. With a two-level atom inside. Okay? And the cavity is set up such that if a single photon enters it, the photon shape is just such that it does a perfect pi pulse and puts the atom from the ground state into the excited state. Okay? So, what is the state of the system at the end? So I start with an input state with one photon in the mode, this mode, no photons in that mode, and the atom in the ground state, both atoms in the ground state. Okay. What is my output state? Well, there's some probability amplitude that it's transmitted. And if it's transmitted, it's a perfect pi pulse. And it puts the atom into the excited state. There's another probability amplitude, which is the photon is reflected. And if it's reflected, it's a perfect pi pulse, and it puts the atom in, that atom in the excited state. So what is the output state? It is a superposition of such. Both photons are gone at that point. And this is either it was transmitted, in which case the first atom is excited, or it was reflected, in which case the second atom is excited. You wouldn't have any problem calling that an entangled state, would you? So indeed, that is a kind of entanglement. And it's the atom is measuring the photon number in that mode. Right? In fact, as we will see maybe, we could use this to do teleportation. The entanglement is a useful resource. We could do quantum teleportation if we had this kind of shared resource with the right kind of measurements. So it's interesting that even linear optics, this is a linear beam splitter, this is linear optics, can lead to entanglement. How is that possible? We just said that entanglement required interaction, right? And linear optics means every photon is doing its own thing. It's not a linear process, but it's really, in some sense, related to this identical particle business. Because if we look at let's look at a beam splitter Hamiltonian. That's a Hamiltonian that generates a linear transformation. So my beam splitter, the old BS Hamiltonian, there's either, I can, if I call these two modes 1 and 2, I annihilate a photon in mode 1 and create it in mode 2 with some amplitude, and I have the Hermitian conjugate. Annihilating mode 2 and creating mode 1. In this case, the amplitude is such that when you exponentiate it, right? Now, notice that this is not separable in mode 1 and mode 2. In some sense, mode 1 and mode 2 are interacting through the beam splitter interaction. So this is an entangling interaction for modes. Not for particles. The particle, each particle does its own thing, but the modes become entangled. This is another thing we've long debated in quantum optics. I think we've now come to believe this is true, this is honest. Now notice, in order to get this entangled state out, the input photon could not be a coherent state. Right? If my input photon was in a coherent state, or any statistical mixture of coherent states, well, let's just say a coherent state to start. If it was a coherent state to start, then the output state would be a product state of you would not get this kind of entanglement, right? You would get, if it was an entangled state, if it was a coherent state, if I had a coherent state 1 and vacuum here, the output state would be the reflection coefficient and the transmission coefficient. I would have a product state in that case. My output state would be transmitted tensor reflected. Right? I would not get entanglement, mode entanglement, if I had coherent states in these modes. What I needed was something with a negative p function. The negative, something which is non-classical in the sense of the p function, like a squeeze state, would end up having entanglement. In fact, that's how you create simple entanglement with squeeze states. You just put it on a beam splitter, and then you have in 2 entangled squeeze modes. Kind of amazing. All right, much food for much thought. Yes, sir?
So is in a sense saying that the entanglement depends on degree of freedom we are interested in?
That's correct. And we kind of saw that last time when we thought about 2 particles, say, connected by a spring. I could have a situation where I have a definite relative coordinate and a definite center of mass coordinate, but entanglement between the individual coordinates of the two particles. So whether I'm thinking about degrees of freedom, particle A, this is not about identical particles, particle A, particle B, or their relative and center of mass, depending on which degree of freedom I'm looking at, it may look entangled or not. And that comes back to the question of ultimately it's what you measure, right? Whether that's useful or not. All right, now I'm going to cheat for the next 20 minutes because there's a lot I wanted to cover, but also some of these things are kind of hard to draw with our current sets of pens and so forth. So I'm going to just show some things from the notes to get just some basic ideas. All right, great. So what I want to talk about now is how, when we saw we could just create entanglement between modes with linear optics. But if we want to create entanglement between particles, we need nonlinear optics. And so we talked about the generation of non-classical light through, for example, three-wave mixing last few weeks ago. And for example, we talked about parametric amplification, whereby we send in a strong pump and we could amplify a weak signal, right? And in the process, we would generate the conjugate idler, which was given by the difference frequency, right? And we saw how, for example, we can get squeezing that way. But we can also, that squeezing is also associated with entangled photons, and it is the canonical source of entangled photons in quantum optics. Now you remember that in this particular case, the idler wave that would come out is the one that would satisfy phase matching, okay, in this three-wave mixing process. So that is, phase matching means that it's kind of energy momentum conservation for the photons. Okay. But we saw that in terms of just Maxwell's equations and how we would get strong amplification of the signal we needed for these waves if we had the sum of the two frequencies, signal and idler, added to the pump, and the wave vectors added together, right? Now, as I say over here, this can be considered as a kind of stimulated emission. So let me just draw a little energy level diagram. Where I have this pump photon, and then I have two photons. So I'm putting in the signal, and I'm getting some extra signal out. And in the process, I also get idler. So I'm off resonance. It's a two-photon process. There's a little aside that I didn't mention before, but it's maybe obvious now. It can't be the case that the material is symmetric under inversion of the coordinates. As to say, the eigenvectors can't be eigenvectors of parity. Why is that? Well, the photon, this can't conserve parity, right? Because the photon is odd parity. You'd have to go from even to odd, but then this wouldn't work, right? Because I have a two-photon process. So that's why it's hard to make materials that do three-way mixing. They have to break inversion symmetry. A gas of atoms cannot be a three-way mixer because the atoms are parity inverting. They do four-way mixing, but not three-way mixing. Anyway, just a little aside there for none of your opticians with it. All right, so that's stimulated parametric amplification. But suppose I didn't put in a seed signal. Then I can spontaneously generate these pairs of photons, and that is known as spontaneous parametric downconversion. Okay? Now, because it's a spontaneous process, there are lots of different ways I can add together Ki and Ks to have Kp, as long as omega I and omega S add to that. There are lots of different processes. And since that works at that time. Almost putting my hands on my hips. You got it. So all of these are possible histories that can happen. And since I don't know which one happened, they happen in superposition. And so that is a kind of entanglement in my two-photon generation. Now, exactly how the photons come out depends on this phase matching condition. This phase matching condition here is, I have to have the two frequencies add together, and then this is just the components of the K vector adding together with the indices of refraction, which are dispersive depending on the signal in either frequencies. Okay? And that determines the pattern around which we do. Now, we said we couldn't satisfy these conditions if the index of refraction was the same for function for both the signal, the idler, and the pump. We needed to have birefringence, where the index of refraction depend on the polarization. There's this whole business of the different types of polarization. Boy, you can really get through a lot of lecture if you just do it this way. Anyway, so the jargon is we talk about type 1 and type 2 phase matching, depending upon whether the signal and either have the same index of refraction function or they are different. They're orthogonal. The signal and the either have orthogonal, one being in the extraordinary and the other being in the ordinary mode. Again, it's not so important, it's just jargon. But the point here is that what we end up is these cones of possible emission patterns that satisfy the phase matching condition. And what we have in this case, in type 1 phase matching, is the two photons have the same polarization. The pump is in the orthogonal, but the two photons that come out, the daughter photons, have the same polarization. But I don't know what color they are. That is to say, one of the dots, so we typically call it the mother photon, the UV, and the daughter photons, infrared. They have to add up to the same frequency of the mother. So it could be that one of the daughters is red and the other is green. It could be that they're both yellow. And if they're red and green, I don't know where they come out on these cones. And that's a kind of entanglement. Yes, sir?
So is this something that has to do with the material properties? Like
Yes.
if you have an isotropic crystal, then
It wouldn't work. Yeah, so it has to have this inversion symmetry breaking. And that's the crystal structure. So, I don't know what it is these days that people use. KTP was periodically, and then there's a whole business of, well, if it doesn't have that, there's a whole business of periodic polling and stuff I don't know very well anymore. But the point is, it's a materials issue, how you get the right inversion symmetry and
do you always get like a cone like that? Is it never like a squished cone or something? Or?
it's so, that's really, yeah. I think it's always like those cones. All right. So, one of the things so I could, for example, put some pinholes and take a sort of narrower bandwidth of photons. Say the photons that come out through that pinhole I'll call the signal photons, and the photons that come out through that pinhole, the islet photons. There'll be some spread in frequency because of whatever the pinhole is, but it could be a pretty big spread of frequencies. Which is to say, each photon is very highly polychromatic. But its sum is definite if this is a very highly monochromatic pump. Okay? And that gives us a kind of entanglement. So here, what you see, this state, I have two photons. One has frequency omega s, the other has frequency omega I. Each photon, this guy is a very big spectrum depending on the size of the pinhole. But the sum of the frequencies adds to the pump. So that's my entangled state. How is it entangled? Well, it's entangled in frequency or energy and in time. That is to say, the photons, well, that should say either, not two. The two photons, I can think about it in the following way. Because of this very broadband process, the two photons are created almost instantaneously together. They're born almost at the same time. I just don't know what their birthday is. Their birthday is uncertain because their birthday depends upon when the photon arrives in the crystal. But if this is a monochromatic beam, the photon is completely delocalized along this axis. So I don't know where the photon mother is, but the mother gives birth, and the process of the spontaneous emission is essentially instantaneous because this is a very broadband process. So there is a kind of, that's a kind of entanglement. This is not a separable state. How could I see that entanglement? Well, one way I can see that is in this kind of experiment. So this is what was known as the Franzen interferometer. What do we got here? I have two Mach-Zehnder interferometers in these two different arms. Okay? They're unbalanced interferometers. So there's a short path by which a photon could go directly to the detector, and a long path whereby it, well, I guess I don't have my beams. It's a theorist beam splitter, sorry. It goes around and comes out that way. The beam splitters are wrong. This one's right. Okay, so there's a short path and a long path. So now we have this process of spontaneous parametric down conversion. The photons are born. We're picking out different directions through these pinholes, and then we let these go to through these two interferometers, and we have a detector. We can look at the counts in either detector, or we can look at the coincidence counts, where both detectors go click at the same time. And we're going to do that as a function of the difference in the path length between the short and the long path. So now let me ask you the following question. If I just look at the singles, that is to say, I look at the number of counts on this detector, right? And if the coherence length of this photon, that is to say, the inverse, but sort of the length of the photon, is much shorter than the path difference. This is a very imbalanced interferometer. What would I see as I slightly vary that path difference? Would I see interference for the singles? The answer is no, because it's distinguishable. Because the photon is such a short wave packet, and that wave packet is much shorter than this path difference. If I see the photon here, I know it went the short path. And if I see it later, I know it went the long path, because those are distinguishable histories. Yeah?
Then you have to know when it was incident on the first group.
That don't really matter it's in the question of interference is whether or not there are two alternatives that are indistinguishable. Because these two alternatives are distinguishable, there is no interference.
So even if you had a second photon that was coming at another time.
That's right, because it doesn't overlap. However, what happens in coincidence? Well, I could have both photons go through the short path, or both photons go through the long path. And since I don't know their birthday, those two alternatives are indistinguishable. Because if I knew their birthday, well, I would know there's no way they could get here, they would get here at a different time than here. But there is an amplitude where the photons were born both photons were born a little bit later, which is in superposition with the photons that were born a little bit earlier. And so I add the amplitudes for those two alternatives. And the way that would work is you would say there's a probability amplitude for both of them to go on the short path, and another probability amplitude for them both to go on the long path. And I have to add them in superposition. And when I square that amplitude, I get interference. And that's a two-photon interference. The interference is only seen in coincidence. It's a two-photon process. The individual photons don't show the interference, but the two photons do, due to that entanglement. And that experiment was done by my friends when I was a graduate student in this lab. I wasn't on the paper, hoo-hoo, but I didn't do anything, so I didn't deserve to be on the paper. But anyway, this was done in Ray Chow's lab by Paul Kwiat and Ephraim Steinberg when they were PhD students in 1993. And what's being shown here are the singles counts as a function of path difference, that's what this prism position is, versus the coincidences which show this two-photon interference. It was one of the first cool experiments that was done. All right. We will take a break for spring break. Of course, you have homework to do. It's not a total break, but hopefully you'll be relaxed for everybody.